Some more examples. So first of all, 50 in unsigned representation will be looking 1, 1, 0, 0, 0, 1. Okay. So this is 1, 2, 4, 8, 16 and 32. 16 plus 32 will be 48. So we need to add 2. It will be 1, 1, 0, 0, 1, 0, 50. In sign and magnitude, we will first write down the magnitude, which is 1, 1, 0, 0, 1, 0, and we will add the sign. Now 50 should be treated like plus 50, and therefore the sign added should be equal to 0. In 1's complement, as it is a positive number, you are not going to complement it. So simply write down the magnitude 1, 1, 0, 0, 1, 0 and add one extra bit for sign. So in sign and in positive numbers will be looking same in sign and magnitude and 1's complement as well as 2's complement. So in 2's complement also plus 50 will be 0, 1, 1, 0, 0, 1 and 0. Okay, so that is plus 50 in all representations. Remember only one thing, that sign and magnitude, 1's complement and 2's complement will need an additional bit for sign. So plus 50 actually can be represented 50, not plus 50. 50 can be represented with the help of only 6 bits, but when you want to write down 50 in sign representation, an extra 7th bit will be needed to accommodate the sign. If you do not write down this 0, then in all the representations, leftmost bit will become 1. The meaning of leftmost bit 1 means negative numbers, and therefore all 3 representations will mean something negative, but 50 is not negative, and therefore all these things are wrong. They will become correct only when you add an extra bit for sign. So 0 is very important when you want to represent positive numbers in sign and magnitude, 1's complement as well as 2's complement. Fine. Now second, minus 50 cannot be represented in unsigned, negative numbers cannot be represented in unsigned. Then minus 50 in sign and magnitude. So magnitude is 50, sign is minus. First of all you write down the magnitude 1, 1, 0, 0, 1, 0 and the sign is negative, so you add 1. Then you in 1's complement, you first of all write down plus 50. Plus 50 will be, it is written already, this is plus 50. Sign bit is important, and then you complement it, so it will become 1, 0, 0, 1, 1, 0, 1. And then you add plus 1 to it. 1's complement plus 1 will be 2's complement. So adding plus 1 to this, okay, I will write it down here. 1, 0, 0, 1, 1, 0, 1 plus 1 will be equal to 1, 0, 0, 1, 1, 1, 1. Okay, so this is how minus 50 will be looking like in 2's complement representation. Okay, we may fall short of space, so I will add plus 1 directly without doing the addition. Fine. So 0, 1 plus 1 will be 1, 0. So it will be 1, 0, 0, 1, 1. Sorry, 0, 1 plus 1 is not 1, 1. It will become 1, 0. So it will become 1, 0. This will be the correct answer. Fine. Now let's talk about 8. 8 in unsigned will be 1, 0, 0, 0. This is 1, 2, 4 and 8. 8 into 1 will be equal to 8. Now in sign and magnitude, you write down the magnitude, which is 8, add plus sign. Similarly in 1's complement, you write down the magnitude, which is 1, 0, 0, 0 and add sign bit. In 2's complement also it will be 0, 1, 0, 0, 0. An extra bit will be needed to represent positive numbers in 1's complement, sign and magnitude and 2's complement. Then minus 8 cannot be represented in unsigned representation. In order to write down minus 8 in sign and magnitude, first write down the magnitude, which is 8, and then you add the minus sign with the help of 1. Then for 1's complement, the plus 8, 1, 0, 0, 0 with the 0 additional sign bit has to be complemented. So if you complement it, it will become 1, 0, 1, 1 and 1. And finally if you add 1 to this, then it will become the 2's complement representation. So add plus 1, it will be 1 plus 1, 0 with carry 1, 1 plus 1, 0 with carry 1, 1 plus 1, 0 with carry 1. So it will become 1, 1, 0, 0 and 0. So 1, 1, 0, 0, 0 will be the correct representation in 2's complement. Fine. The next example, the final one, is 31 and minus 31. Now 31 in unsigned representation will be represented by 1, 1, 1, 1, 1. 1 plus 2 3 plus 4 7 plus 8 15 plus 16 will be equal to 31. In sign and magnitude, the magnitude will be 31 and the sign will be plus. Same will be 1's complement 0 1 1 1 1 1 and same will be 2's complement 0 1 1 1 1 1. Now in unsigned representation minus 31 cannot be represented. In sign and magnitude minus 31 will be 31 followed by the negative sign which is 1. Then in 1's complement this plus 31 has to be 1's complemented. This plus 31 0 is important, don't neglect it, and now do the 1's complement. It will be 1 0 0 0 0 and 0. Every individual bit has to be complemented, and finally 1's complement plus 1 will be equal to 2's complement, so it will become 1 0 0 0 0 and again 1. 5 times 0 plus 1 will be equal to 4 times 0 1. So this is how minus 31 will be looking in sign and magnitude, in 1's complement as well as in 2's complement. Fine. Now in the next part we will be seeing how these values have to be interpreted, okay, or what are the various place values in unsigned, sign and magnitude, 1's complement and 2's complement. See, what do I mean to say here? In unsigned representation the place values are 1 2 4 8 16 and 32. Here the place values are 1 2 4 8 16 32 and sign. Here the place values are 1 2 4 8 16 32 and this sign will be minus 63. Okay, what we will do, we will take a separate example and we will see what are the various place values in the different representations. So for that what I will do, we will copy minus 31, minus 8 and minus 50 and then we will see the next important concept. Okay. So let me write down all the values. Minus 50 is equal to 1 1 1 0 0 1 0 in sign and magnitude. Okay, fine, we will take only one example. In sign and magnitude it is like this. Then minus 50 is 1 0 0 1 1 0 1 in 1's complement and it is 1 0 0 1 1 1 0 in 2's complement. Fine. And plus 50 is equal to 1 1 0 0 1 and 0. Now see, in unsigned plus 50 is written as 1 1 0 0 1 and 0. Now every place will be having a value, and as we have seen in the numbers, in number system, the place value of this base, the rightmost digit will always be 1, and because it's a number base 2, so the corresponding place will be multiplied by, place values will be multiplied by 2. So next place value will be 2, then 4, then 8, then 16 and then 32. And then you multiply the place value with the corresponding digit to get the total value. So 32 multiplied by 1 will be equal to 32 plus 16 plus 0 plus 0 plus 2 plus 0. So if you do it, 32 plus 16 plus 2 comes out to be equal to 50. So what I mean to say, every place will be having a corresponding place value. So the places where 1's are there will be added, and the places where 1's are absent, zeros are present, should be neglected, and this is how the value of any particular bit pattern can be calculated in unsigned. Okay. Then as far as other representations are concerned, now you should note the place values. Okay. The place values are 32, 16, 8, 4, 2 and 1. So this is unsigned representation, this one. Fine. Now in signed representation, one more bit is present and that bit is 1. Okay, minus 50. So place values are not going to change, place value will remain the same. So it will become 1, 2, 4, 8, 16 and 32, but the 1 should be treated as minus and 0 should be treated as plus. So there is no concept of place value here, simply 1 means minus sign and 0 means plus sign. Instead of writing down the sign, you will write down the 1 as a bit. Okay. Now more important thing is the case of 2's complement. Okay. Now in 2's complement, the number minus 50 is written as 1 0 0 1 1 1 0. Okay. Now if you take the place values like unsigned, the place values will be, treat this pattern as an unsigned number, as a simple binary number, and take the place values. So place values will be 1 2 4 8 16 32 and 64. However, because we know that the given number is present in 2's complement representation, the last bit represents sign bit, and therefore the value of last bit should not be taken as 64, instead it should be taken as minus 64. And now see the magic, if you add all the numbers, if you apply the formula summation of face value multiplied by place value, or summation of digit multiplied by place value, you will get the desired number. See, 1 multiplied by minus 64 is equal to minus 64 plus 32 into 0, 16 into 0, 8 into 1 will be equal to 8, plus 4 plus 2 plus 0. So it will be minus 64 plus, now this addition will come out to be equal to 14. 8 plus 4 12, 12 plus 2 will be equal to 14, and minus 64 plus 14 will be equal to minus 50, and this is the number that we want to represent it in 2's complement representation. Okay, so what I am trying to focus on, instead of simply concentrating on how to write down minus 50 in 2's complement representation, you should also focus more on what the individual place values will be as far as 1's complement, 2's complement representations are concerned. And remember me, these many place values are not going to change, they will remain the same. The last place value will change as far as 1's complement and 2's complement representations are concerned. And okay, now this is about 2's complement representation. And finally, in 1's complement representation, instead of going for minus 64, you should treat this value as minus 63. And if that happens, okay, wait. We need to take the 1's complement number first. Okay, in 1's complement, the number minus 50 is written as 1 0 0 1 1 0 1. Okay, 1 0 0 1 1 0 1, 1 0 0 1 1 0 1. Now take the place values like 1 2 4 8 16 32 and 64, as if the number is an unsigned number. Now because we know it's a 1's complement number, the last bit should be treated as negative bit, sign bit, it's 1, therefore instead of minus 64 you should go for minus 64, but minus 64 will be there in 2's complement. In 1's complement you decrease it by 1, so instead of 64 you should make it minus 63. So what we are doing, we are decrementing both the sides by 1. So see, now again apply the formula summation of digit multiplied by place value. Minus 63 multiplied by 1 will be equal to minus 63 plus, let us see what is the addition here, 32 into 0, 16 into 0, 8 plus 4, earlier it was plus 2, now it is plus 1. So 8 plus 4 plus 1, okay, will be equal to minus 63 plus 13, which comes out to be equal to minus 50. So what I am trying to say, in 2's complement you should go on writing down the place values, last place value should be negated. Okay, so 1 2 4 8 16 32 and minus 64. In 1's complement it should be 1 2 4 8 16 32 64, make 63 and then you negate it, so the last place value will be equal to minus 63. Now what is the advantage of this particular scheme? See what happens. Say you want to write down minus 60. Okay, so what I will do, I will take various places 1 2 3 4 5 6 7, say, and we will take the place values. Now place values will be 1 2 4 8 16 32, and let us suppose we want to write down minus 60 in 2's complement. Okay, so what I will do, in 2's complement we know that the last bit will always be equal to minus 64. Fine. Now because we want a negative number, I will put a 1 sign here, so it becomes minus 64, but I want minus 60. So in order to bring down minus 64 to minus 60, actually you are not bringing down, you are bringing it up. You need to add 4. So how 4 will be added? You put a 1 here and make all other bits equal to 0. So it will become, see, very simply you can convert minus 60 in 2's complement, and you add them, minus 64 plus 0 plus 0 plus 0 plus 4 plus 0 plus 0. Minus 64 plus 4 will come out equal to minus 60. Okay. Similarly, if you want to write down, say 0 or say minus 128 in 2's complement representation, then what you will do? Again you go for multiple places. 1, 2, 4, 8, 16, 32, 64, and here you go for minus 128, because if you simply put a 1 sign here and zeros everywhere, then the resultant addition will be equal to minus 128. You can see minus 128 into 1 is minus 128 plus 0 plus 0 plus 0 plus 0 plus 0 plus 0 and so on. And likewise you can go on converting the value. For example, if you put 1 here, then it will become minus 128 plus 8. So this particular value will become minus 120. If you want, say 100, minus 100, then you subtract 28. How will you subtract 28? You subtract 16 plus 8, 24 plus 1. So if you want to represent minus 100 in 2's complement representation, what I will do? We will write it down like this. This is minus 128. Now we want additional 28, so that minus 128 plus 28 becomes equal to 100, minus 100. So in order to construct minus 28 plus 28, what I will do? I will make it 1, that is 16 plus 8, 24 plus 4, 28. Now if you add all these numbers together, it will lead to minus 100. See, minus 128 plus 16 plus 8 plus 4 will be equal to minus 100. And similarly, if you make all ones, then the result will always be equal to minus 1. Okay, so see how this is minus 128, and if you add all these numbers together, they will add to plus 127, and minus 128 plus 127 will be equal to minus 1. So whenever you write down all ones in 2's complement representation, the value will always be equal to minus 1. Remember it very well. If I ask you what is the value of 1111 is 2's complement, don't think it will be equal to minus 1, because the place values will be 1, 2, 4, minus 8, and minus 8 plus 7 will come out to be equal to minus 1. And take it for any number of bits, it will always be satisfied. For example, if you take 1, 1, 1, 1, 1 in 2's complement, that is equal to minus 1. Why? 1, 2, 4, 8, add them, this will be equal to 15, and this is minus 16. Minus 16 plus 15 is equal to minus 1. Add one more bit, 1, 2, 3, 4, 5, 6, 7 for example. Do it like this, 1, 2, 4, 8, 16 and 32. The addition here will come out to be equal to 63, and the last bit will be taken as minus 64. Minus 64 plus 63 will again come out to be equal to minus 1. Go for 8 bits, doesn't matter. 1, 2, 3, 4, 5, 6, 7, 8. The place values will be 1, 2, 4, 8, 16, 32, 64, and the last place value will be minus 128. Add all these numbers together, the result will be equal to 127. Minus 128 plus 127 will again come out to be equal to minus 1. And what is the fundamental property? Important fundamental property, all ones in 2's complement representation means minus 1 always. Fine. And this is how it is going to work. Now, what we will do, we will try to see how a particular bit pattern can be interpreted in various representations. See, right now what we have seen how minus 50 can be represented in various representations. Minus 15 sign and magnitude, minus 15 1's complement, minus 15 2's complement. And now what we are going to do is the reverse process. We will see how a particular bit pattern can be interpreted in unsigned in sign and magnitude in 1's complement and in 2's complement. Okay, so let us see what I am trying to say. For example, the bit pattern is 1 1 0 1. The given bit, if I ask you what is the value of 1 1 0 1, you cannot tell the exact value, because the exact value will depend upon interpretation in what scheme it has been written. See, let me give you a simple example, very simple example. If I ask you what is this, okay, somebody may say 10 if interpreted in decimal, somebody may say 2 if interpreted in binary, somebody may say 16 if interpreted in hexadecimal, somebody may say 8 if interpreted in octal, and so on and so on and so on. What I am trying to say, you cannot tell the exact value of 1 0 unless and until you don't know the representation, you don't know the scheme which has been used to write down 1 0, unless and until you don't know the number system, the base, the radix which is used for writing down 1 0. So there are certain things that you need to know, and that's why a given bit pattern can be interpreted differently in different formats. Therefore, what I will say, what we will do, we will take one bit pattern and we will see its 4 different meanings that can be drawn. So 1 1 0 1 in unsigned means 1 plus 2 plus 4, sorry, 1 2 4 8, it will be 8 plus 4 plus 1. Now 8 plus 4 plus 1 comes out to be equal to 13. So it means 1 1 0 1 in unsigned means 13. Fine. Now if you want to convert the same bit pattern in sign and magnitude, if you treat this bit pattern as a sign and magnitude representation, then it will be sign and magnitude. Now sign is minus because of this 1, and the magnitude is 1 0 1, which means 5. So 1 1 0 1 in sign and magnitude means minus 5. That is quite simple. Okay. Now to find out the value of 1 1 0 in 1's complement, what we will do? Okay, first of all we will calculate in 2's complement. In 2's complement the place values will be 1, 2, 4 and minus 8. Now if you add them together, this will be minus 8 plus 5, and minus 8 plus 5 will come out to be equal to minus 3. So 1 1 0 1 in 2's complement means minus 3. And if you want the same thing in 1's complement, then you take the value as minus 7, and minus 7 plus 5 will mean equal to minus 2. So 1 1 0 1 means 13 in unsigned, means minus 5 in sign and magnitude, minus 2 in 1's complement and minus 3 in 2's complement. Okay, you should be very clear with this. And see, there is one more way to achieve this conversion. If you want to convert, if you want to treat this value in 1's complement, what you do, you again take the 1's complement of 1 1 0 1. So 1's complement of 1 1 0 1 will be 0 1 0 1. Sorry, 1's complement will be 0 0 1 0. Now the original sign bit is equal to 1, therefore you write down the minus sign, and the magnitude comes out to be equal to 1 0, which means 2, therefore minus 2 will be the value, and you take the 1's complement again, then it will be equal to, sorry, you take 2's complement of 1 1 0 1. So 1's complement will be 0 0 1 0, plus 1 will be the 2's complement, that is 0 0 1 1. The magnitude comes out to be equal to 3 and the sign will be equal to minus. So it will become minus 3. Okay, now this will become clear in further examples. Say 1 0 0 0 1 in unsigned. Okay, let me write it down. 1 0 0 0 1. In unsigned it will be 1 2 4 8 and 16. So 16 plus 1, this becomes equal to 17. In sign and magnitude, the sign will be 1, which means minus, and the magnitude will be equal to 1, so it means minus 1. Now for converting this value to 1's complement, what we will do, we will not follow the place method, we will follow the direct method. See, the leftmost bit is equal to 1, that means the original number is a negative number. Okay, and in order to find out the magnitude, you take the 1's complement of this number. the 1's complement of this number will be 0, 1, 1, 1, 0, and the value of 0, 1, 1, 1, 0 means equal to 14. Fine. So it means it is minus 14. Then if you want to convert this pattern to 2's complement, you again take the 2's complement. So the sign is minus, you write down minus, and in order to find out the magnitude, you take the 2's complement. So 1's complement will be 0, 1, 1, 1, 0, plus 1 will be the 2's complement, 0, 1, 1, 1 and 1. 0, 1, 1, 1, 1 means minus 15. And you know, you can observe whenever you interpret any particular bit pattern in 1's complement and 2's complement, then the value in 1's complement will be 1 more as compared to the 2's complement. Fine. Then next, say it is 1, 1, 1, 1, 1, or we will take all ones. Let us go for all ones. Now all ones, here the meaning will be equal to 15. In sign and magnitude, it will be like this. Sign is minus, magnitude is 7. So it will become minus 7. In 2's complement, we will use the place value 1, 2, 4 and minus 8. Minus 8 plus 7 will be equal to minus 1. And in 1's complement, this place value should be taken as minus 7. So minus 7 plus 7 will come out to be equal to 0. Okay. Then next bit pattern we will take 1, 1, 1, 1, 1, 1, 6 times. Now in unsigned, it will be equal to 1 plus 2 plus 4 plus 8 plus 16 plus 32 equal to 63. In sign and magnitude, it will be minus 31. Okay. In 1's complement, it will be equal to, what will be the place values in 1's complement? This will be 1, 2, 4, 8, 16, 32, reduce it by 1, make it 31 and minus 31. So minus 31 plus 31 will come out to be equal to 0. And in 2's complement, this place value should be taken as minus 32. Minus 32 plus 31 will come out to be equal to minus 1. Again, one observation from these two values, that all ones in 1's complement means 0 and all ones in 2's complement means minus 1 always. Okay. So these observations are quite important. And let us see some more example. Say we got 1, 0, 1, 0, 1, 1. Now 1, 0, 1, 0, 1, 1 means, okay, let us see, 1 plus 2, 3 plus 8 is 11 and 11 plus 32 means 43. Let me check it again. I will write down the place values 1, 2, 4, 8, 16 and 32. So 32 plus 8 is 40 plus 3 is equal to 43. Now same thing in sign and magnitude means minus, and 0, 1, 0, 1, 1 means 11. So it means minus 11. Fine. 1, 0, 1, 1 is 11. Then in 1's complement, the place values will be 1, 2. Okay, what we will do now for 1's complement, we will apply the second method. We will take 1's complement of this number to get the decimal value in 1's complement. So what we will do, sign bit is 1. So I will write out the minus sign. And in order to find out the magnitude, we will take 1's complement of this number, which will be 0, 1, 0, 1, 0, 0. It means 16 plus 4 equal to 20. So the value will come out to be equal to minus 20. And in order to find out 2's complement, 1 will become the minus sign, and in order to find out the magnitude, you will again take the 2's complement of the given negative number. So this is 1's complement plus 1 will be equal to 2's complement, 1, 0, 1, 0, 1, which means minus 21. So what is the most important lesson that you need to learn from these examples is that a given bit pattern means different things in different representations. So if somebody asks you what is the value of this particular representation, what is the meaning of 1, 0, 0, 0, 1, you first ask a counter question, what representation has been used, and then only you should give the exact value. Values depend upon the scheme which is used for representation. Thanks.